knows Charles Singh. He's been president of the International Society. He's one of the most remarkable researchers around. He's a professor of civil and environmental engineering at Hong Kong University of Science and Technology. He's also the dean there. He is a chartered civil engineer, fellow of the Royal Academy of Engineering, and a fellow of the Hong Kong Academy of Engineering Sciences. He was also elected as Overseas Fellow by the Churchill College of University of Cambridge. He has supervised more than 55 PhDs and 60 MPhil students, and more than 350 journal articles and 250 conference papers. He is the author of 3 very valuable books, short course on soil structural engineering on deep foundations, excavations and tunnels, advanced structural unsaturated soil mechanics and engineering, and the third one is a unique one, plants soil slope interaction. And I would now like to invite Charles to give his talk, which we have been all looking forward to. Charles?
Thank you, my friend Madhav. Long time no see. I can see you are very happy and healthy.
We are hoping to get you to India, but looks like the COVID kept you away.
Yeah, that's right.
I've been wanting you to come for quite some time.
Thank you. But so far, I've been to India 4 times already. Yeah, certainly I'm looking forward more. But unfortunately, the pandemic, I couldn't travel, obviously. Yeah. Thank you for a kind introduction. And so if I may share my screen, I open the PowerPoint now.
Yes,
okay.
Yes,
and
it has come.
It has come, good.
And then sharing.
Go ahead.
Okay. Can you see anything?
No, not now. Now it's okay.
Now it's okay. Back to normal. Yes?
Make full screen, yeah.
Good. Okay. Thanks. Okay.
Welcome. To make it full screen, sir.
Yeah, I will. I'm doing now. Yes.
Yes, sir.
Okay. Okay. Sorry for the delay, and thank you everybody for waiting patiently. And this is the title of my presentation, and the new novel environmentally friendly vegetated 3-layer landfill cover system using construction waste, but without geomembrane. And I'm sure probably most of you know that, or almost all of you know that, normally for landfill cover, people use a geomembrane. Right? And I'm going to propose a new one without using a geomembrane based on unsaturated soil mechanics. So here's a table of contents on my presentation. First of all, if you allow me to give a very quick introduction of my university, because some of you may be interested, and later on you'll know why, and then research background, and then theoretical considerations of this new 3-layer cover system without geomembrane. The important keyword is all weathered, okay? It's not in dry, arid region, but also in wet region like in Hong Kong. And then I'll report to you about our one-dimensional soil column tests, focusing on the effects of vegetation, and also using of recycled concrete without geomembrane. And then I'll report to you a long-term monitoring, which is lasts for 4 years on an actual landfill site in mainland China, and using recycled concrete without a geomembrane. Okay, and across the border of Hong Kong, that means also in a humid climate. Then finally, I'll go to conclusion and deliverables. Just very quick about my university, and was established in 1991. And we have 4 major schools, roughly 10,000 undergraduate students and 5,500 postgraduate students, including 3,500 MSc students. And we have a pretty big geotechnical group, consists of 60 about PhD students currently, and also 30 MPhil students. Here are just a couple of pictures showing different views of our campus. And I hope you do agree it's pretty beautiful. And I would like to extend my open invitation to all of you here. If you do come to Hong Kong, drop me an email, and you're most welcome to visit us. And I would invite you to give us a talk to our students or to our faculty members. And although we are young, but we are highly sort of rented in terms of 2, say, largest ranking agencies in the world times higher education. For young university means over the age of below 50. Then we were number 1, and QS went as number 2 in the world. And I will not go into detail for other rankings. Okay. And one new things I want to report to you all, and as I say, you may be interested, we are building a new campus, which is about 2 times the size of our current campus, and is located in Qingsheng here. And this is Kowloon's Kowloon West Station. If you catch a fast speed train from Kowloon West to Qingsheng, it only take 27 minutes. 27 minutes. And the official language over there, although in mainland China, still is English. Just like we are here in Hong Kong, our official language is English. So in other words, if your students in India willing to come to Hong Kong for exchange, okay, or even reading a degree, and this is most convenient, put it that way. And this is a couple of views, okay, about our new campus. Again, it looks very beautiful. Actually, it's by a river, this time not by a sea, by a river. And it's under construction now. And the campus will be, phase 1 will be completed in September 2012. That means less than 1.5 years from now. And we are going to have 6,000 postgraduate students, mainly research students, in the first 6 years. And then from year 7 to 10, we'll have 4,000 undergraduate students. So this is another view of the campus, okay, of the new campus in Guangzhou. As I said, the size of the new campus is twice the size of Hong Kong campus. But the style is sort of very similar. We have a red sundial in the middle. Now, the important thing is we encourage, okay, exchange programs, meaning, for example, IIT from India can have an exchange program with us. Then we provide scholarship for students. I'm talking about postgraduate students now, and say about $1,200 per month for visiting up to 6 months. But for full-time research students in our campus, the scholarship ranging from slightly about $2,000 to $3,500 per month. And also we offer dual degree PhD programs, meaning we can have dual degree between 2 universities, any one university in India and with us. Of course, the develop a dual degree program, it takes time a bit, okay? Now, this is a typical group, a typical time of my group, okay? And what you are seeing here, actually, my group is pretty big, including research assistant professor and also postdocs, and from 17 countries. So from, for example, South Africa, and this guy here is from UK and Bangladesh, Thailand, and actually one from India, and he graduates last year, and Iran, for example. So my group is very international, and any student or any professors in the audience, if you're willing to consider to collaborate, do contact me. All right, so let's move on to the lectures today. So background, we all know that landfilling is still at the moment one of the key solutions for municipal solid waste, okay, MSW. And if we want just to review what's the function of a final cover, at least serves 3 mechanisms, okay, or 3 functions: prevent water infiltration, minimize gas emission, and also must be environmentally friendly. Here, just a typical current or modern landfill cover. I'm going to show you on the left-hand side here, a vegetated topsoil, and also a sort of engineered soil layer for the plant to grow, and then a composite drain, and the geomembrane. Okay, that's the material I'm proposing. We can get rid of it, okay, to minimize a lot of problems. And then below that is a compacted clay layer, and then gas collection, and then solid waste. And I'm sure you all know that, okay, many failures at the interface being reported around the world, okay. And by the way, this is the one also in Xiaping, in Shenzhen, just across the border from Hong Kong, okay, in the very southern part of China, mainland China. So you can see again, an interface failure there. And actually, interface instability problem and susceptible to defects, holes of the geomembrane, durability, and also desiccation cracks in the clay here. And high maintenance costs have been widely reported more than 30 years ago, okay, widely around the world. And a little bit background, I don't know what happens in India, but this is just the composition of waste in Hong Kong. Okay, about around 25% of our solid waste actually come from the construction industry. Okay, we call construction waste. That's the data from 2016, and actually there's not much change over the years. So obviously, construction waste is a major problem these days, and occupy 25% of the space of a landfill. So another question is, can we make our final landfill cover, okay, more robust and also environmentally friendly? Can we consider to use construction waste again? Okay, recycle them, okay, put back as a landfill cover. Okay, so let me repeat. Can we use concrete construction waste, break them into different particle size distributions, and then put back as to form a landfill cover without the use of geomembrane? So to summarize is to use waste to cover waste. That's the idea. Very simple. Of course, by thinking about that, we have make use of unsaturated soil mechanics. And that was a book I published in 2007. And make use of unsaturated soil mechanics, then we can do something, I believe. Okay. So let me introduce an excellent concept introduced in the 90s in US. It's called CCBE, capillary cover barrier effect. And in effect, it's based on unsaturated soil mechanics, although the intention was used for arid and semi-arid region. So the idea is when rains comes, we have fine-grained soil on top, and then the permeability of the fine-grained soil is more permeable than the coarse grain below. Then you might think I'm crazy, what I'm talking about. If based on saturated soil mechanics, the concept is absolutely wrong, right? But for unsaturated soil, it's different ballgame. So let me emphasize that this is for unsaturated cover. And I do believe nobody will build a final cover system, saturate the cover system. So this is unsaturated phenomenon. So in other words, this is less permeable. Then if I try to explain this diagram to using a permeability function here. So what you are seeing here is a water permeability versus matrix suction. So in the arid and semi-arid region, that's in certain parts of US, then the annual rainfall less than 800 mm per year. And because it's unsaturated, for a given suction, if you draw a vertical line up, actually the coarse material has a lower permeability than the fine-grained soil. Why? Because the coarse material has more air. Air is not a conductant to water. Okay, so let me repeat in the unsaturated zone. Okay, in the unsaturated zone, coarse material has a lower permeability than the fine-grained soil. That's exactly been used, so-called capillary barrier effect, what you can see on the left-hand side here. Now, our traditional saturated soil mechanics is fine-grained soil has a lower permeability. Sorry, coarse-grained material has a higher permeability than the fine-grained soil. Okay, you are absolutely right when you considering the soil is saturated, but on the unsaturated zone, it's just the opposite. So the question is, can we use this characteristics, okay, to form a new all-weathered final cover? Now, for this case, obvious cannot be done because when the any rainfall over 800 mm, of course, the number 800 or 700 or 900 is just for illustrative purposes. Then this CCBE two-layer system will break down. It will not work. Okay, so it will not work for humid regions like Hong Kong, Singapore, Malaysia, and southern part of China. So what can we do? So the idea is, why can't we add one more layer at the bottom? So when the first two-layer CCBE has been broken by infiltrated water, then make use of the low permeability soil. So if I may illustrate here, this is a traditional two-layer CCBE. Then if I add one more layer, okay, here in red, then what you can see, the stopping water getting through to the landfill when the soil or the landfill, sorry, when the cover is pretty dry, then use coarse grain soil. But when you come to the humid region, like in Hong Kong or Malaysia, Singapore, then actually rely on this red line. Okay, that's the function of this low permeability soil, in addition to the previous two layers. So that's why I call three-layer all-weathered unsaturated landfill cover system. One additional advantage of putting this layers, low permeability soil, low means obvious, means very fine grain soil. There's an additional benefit is to prevent or minimize gas emission, okay? The whole idea is no membrane should be required. By the way, for the two-layer system, also for the two-layer system used in the United States, in arid and semi-arid region, membrane was used. Okay, and what I'm proposing now is no membrane is required. Of course, I have to prove, okay, both theoretically and also experimentally. So essentially, it's adding one layer to cover this region, humid region. Now, talking about gas emission, actually we did tests even and also published in 2015 on waste management and also Vital Zone Journal. Okay, using this low permeability soil, fine grain soil, to resist gas pressure, and actually, even can up to, if you use pure clay, then actually up to 50 kPa. Okay, and of course the breakthrough pressure depends on the degree of saturation of the clay, and we can change to other finer material. You can see here, fine soil and even coarse soil. Typically, the gas breakthrough pressure is higher than 10 kPa, and I'm sure some expert in the audience, you know the emission pressure during the final stage of the covering, okay, so-called final cover. The construction of final cover, the pressure is pretty low, typically less than even 1 kPa. So this bottom layer is sufficient, okay, even without using a geomembrane. But anyway, if you're interested, there are 2 papers there, and you're welcome to take a look for details. And today, obviously, we don't have time to go to that. Anyway, so our proposed 3-layer system together with vegetation, and then we decided to use a 3-way approach. One is a field test, and I'm going to report to you very soon. And then physical modeling, including 1D soil column, and I'm going to report, and then 2D 3-meter long flume. But unfortunately today I don't have time to go into that. And also theoretical and numerical modeling. Again, we have done that, but no time to go into that. So these are the two I'm going to focus. Okay. I think I guess probably another 15 minutes. All right. So experimental setup. So today I'm going to show you two series of tests. One is called V1 and the other one V2. And V1 is used so-called if a laboratory material, silt, guavuli sand, and clay. Okay. And we have a comparative test, one with and one the other one without, okay, vegetation. And V2 series is using recycled concrete. And the material, instead of using silt, we use fine recycled concrete. Instead of guavuli sand, we use coarse recycled concrete. Instead of using pure clay, we use natural material can be found on site. So complete decomposed volcanics. Okay, so the idea is to study recycled concrete as a substitute. And for the test we conducted, we also put plants on top. Now, talking about the particle size distribution of the material I just mentioned. So the black one here, okay, is what we are very familiar with, so laboratory clay, if you like, okay, kaolin clay, and this is a silt, and this is the CDV, completely decomposed volcanics, and the green one is CDG, and this one here is a fine recycled concrete, FC. Okay, FC is here. Okay, recycled concrete. And this one here, triangle, is guavuli sand. And this one here is CC. CC is here. Okay, coarsely recycled concrete. And this is CDV. Okay, you may call it clayey silt. So those are the material we use in our experiments, both in the lab and also in the field. Now, this is one typical setup, and the 1D column is 1.6 meter in height. And then typically we have a 3-layer system here, clay for this one, V1 series, okay, guavuli sand, and the silt. And then depends on whether we study vegetation or not. Okay, for this one here, you illustrate with we plant struts inside this column, and we let it grow for 3 months. Okay, and then we start the experiment. And within the soil column, we install quite a number of instrumentation, like a small tube tensiometer, a volumetric water content measurement device, and so on. And we applied a constant head using this Marriott bottle. Okay, and typically it's 0.1 meter constant head, and then measure water content change inside the column, and also suction change inside the column, together with any water coming out from the bottom. Okay, so the bottom is a free drainage arrangement. So this is a schematic diagram for V2. And V2, the setup itself is identical except the material used. Okay, instead of using laboratory material, we use FC, okay, and then CC and then CDV. They are recycled concrete here. Okay, of course they crushed to different particle size distributions, and you have seen early on. And then again, depends on need, we put plants on top. So this is the actual picture for one of the series V2 tests. So on the left-hand side here is a bare, okay, no vegetation, and then in the middle is a Sophora arboricola, and the last one here is a Canodon sedaton, and actually it's a grass, okay, and this is a shrub or tree. Sorry, this is a tree. This is a grass, okay, and what you're just about to see, I think, and here is a recycled concrete FC, okay. And then this layer is a coarse or poorly graded recycled concrete, okay. And the bottom here is completely decomposed volcanic soil, okay, CDV so-called. Again, now let me remind everybody, for all our 1D column tests and also for the field tests, no geomembrane whatsoever has been installed. So no membrane whatsoever. So let's see the result from V1. And this is silt, gravelly, sand, and clay. And this is the initial suction before we applied ponding. Okay. And when we expect, okay, and this is a vegetated, that means with a plant there. And when we expect higher suction, because plant suck in water to induce higher suction compared with the bare one. Okay, bare one is just evaporation. This is evapotranspiration. So this is exactly what we expect. We give a high suction. Then we apply ponding, 0.1 meter of water head on top ponding. And for how long? For 8 hours. Okay. And then you can see this near the top, the suction immediately destroyed. So the red line here is the measurement after 8 hours of ponding. And the black one is also after 8 hours ponding, but from the bared column. So the important point to note is here in the gravelly sand layer, actually the soil or the water did not break through. So the two capillary barrier effect works without geomembrane. Water did not break through. Okay. And one can also see the measurement in clay. You can see the suction. Okay. There's not much change. So suction, for both tests, suction did not return to 0. So that means there's no water. So we base on major suction measurements, and also physically we measure, see whether any amount of water coming out from the bottom. Again, there's no water coming out from the bottom. So that is a clear proof. And what does it mean? What does it mean by 8 hours ponding? Actually, based on agricultural science, guys, there's an empirical formula. We can convert the 8 hours of ponding should be equivalent to 60-year return period of rainfall in Hong Kong. Okay. Now, Hong Kong typically have about 2,500 mm per year. So Hong Kong is pretty wet. That's why it's a humid region. So 60-year return period of Hong Kong's wet weather means a lot of water. Now, how about V2 using recycled concrete? All right. So we repeat the same procedure. Remember, there's 3 columns. I show you the picture. So the black one is the bare, okay, and the blue one is the grass, and the red one is the straw. Okay, so those are the measured result immediately before ponding. And again, when we expect vegetated columns to give a higher suction because the plants suck in water, not just evaporation, but evapotranspiration. And also from this data, you can see actually the struts suck in more water than the grass. Then after ponding for 48 hours. Now 48 hours instead of 8 hours early on. So the one with vegetated with struts, okay, is the red, use the same color code. The blue one, actually is all the suction disappeared, okay, in strut, except at the bottom here in the CDV layer, okay. But in the CC layer, okay, coarse-grained concrete, coarsely crushed concrete still have a bit of suction, about 5 kPa. And the bare one, almost all suction destroyed, okay, except in CDV. Now, the important point to note is in this CC layer, okay? CC layer, the 2 columns vegetated with struts and also grass still will maintain fairly high suction, okay? That means the permeability in CC in this CC layer is still pretty low. Okay, that explains why actually after test we did not measure any water come from the bottom. Okay, even for the bared one, you can see the suction still is about 17 kPa. Okay, so after ponding for 48 hours, meaning what? Meaning equivalent to over 1,000 year return period. Okay, so it's a very heavy rainfall, in other words. Okay, so those are the physical measurements. Okay, 1D column obviously is, as the name says, 1D is probably the most critical condition for a landfill cover. Sloping ground of a landfill certainly is not as severe as the flat ground, means 1D column. But anyway, so this is the result, okay, from small tube tensiometer. Now, actually, we have a water content measurement. The results are consistent with the suction measurement, so I will not go into detail in the interest of time. Again, okay. So now let me move on to field tests. I'm sure many engineers will say, come on, this is only laboratory testing. Why should I trust you? We like to see field data. Okay, so that's exactly what we have done for last 4 years. So our objective is to verify the effectiveness of the proposed 3-layer landfill cover system using construction waste under natural climate conditions, means under subject to rainfall, or natural rainfall. Okay, and also to compare bare and vegetated 3-layer landfill cover system. So this is the landfill site, and we carry our experiment, and actually the Xiaping landfill site actually is one of the largest landfill in China. Okay, design capacity is about 47 million cubic meter. Okay, and the construction actually was divided into 2 phases. Okay. So this is the location of our test site given by the owner of the site. And there's a flat ground here for us to study a biochar and so on and so forth, and plant density, and this here, and also study biochar, but sorry, this one is for plant density, this one for biochar, and this one is for our landfill experiments. Okay, and what you just actually you can see on the left hand side is a bare, on the right hand side is a grass, and the width of this site here is a 12 meter, and the length is 20 meters. So altogether it's about 600 meters square. Okay, and the slope, the angle is around 30 degrees. Okay, so sorry, so the material we put in as a cover is unsifted, complete decomposed granite. So it's a silty sand. Okay, unsifted. So the one here, what you can see in blue. Okay, CC is a coarse recycled concrete. What you can see here. Okay, very coarse material here. Okay, and sifted CDG is this one here. Okay, so this is sifted CDG. Now let me emphasize, all this material are locally available. Okay, that's we, instead of using other material, because obviously if we can use local material, which will be much cheaper for construction. So this is how it looks. Okay, the slope angle is 30 degrees, and this is the bare side, and this is the vegetated side, and we plant Bermuda grass because this is widely available in the southern parts of China. Now, a little background about the weather condition in Shenzhen. Okay, the annual rainfall cumulatively is over 2,000 mm. Okay, and then annual potential evapotranspiration is around 1,000. So in other words, there's a net water flow upwards. Now, again, no geomembrane have been used on this field trial. And here's just a cross section. Okay, with you have here this upper layer here is unsifted, complete decomposed granite, and then coarse recycled concrete, and the sift complete decomposed granite. And Along the depth, we install quite a big number of instrumentation there, okay, including jet fuel tensiometer, measure moisture probes, gas pressure transducer, and even settlement plate. And perhaps the most important I'd like to highlight only report today is the lysimeters. Okay, we install altogether 6 lysimeters to collect water shipping through, okay, to this location. There are 3 locations. That's on the cross section. And also, if you look at the plan view, okay, earlier you see a cross section XX, now we see a plan view. So we have 2, okay, near the crest, 2 lysimeters, and 2 in the middle, and 2 at the bottom. Okay, and that's, to me, I think this is the most reliable mechanical measurements. So we know exactly the amount of water getting in, okay, or not. Okay, so those are the instrumentation installed on site, and in the interest of time, I cannot go to detail. So this is a lysimeter. We use 1 meter in diameter. Okay. Now the data. So here is a daily rainfall record, okay, since June 2016, and to the end is June 2020. So slightly over 4 years. So the green lines are the daily actual rainfall, actually we measure on site. And the black one is accumulated. So over the 4 years, the cumulative rainfall is over 8,000 mm. So as I report to you all, roughly in Shenzhen that region, and any rainfall is over 2,000. So it's a normal condition, put it that way, okay, and typical humid condition. All right, so now let's see the result, okay. And what you're going to see here is a cumulative percolation measured by the 6 lysimeter, okay.
Charles, can you kind of...
Excuse me, Professor.
Yes.
You got another 5 minutes time, please.
Yeah, no problem. Yeah.
Yeah, thank you.
And on the right hand side is a daily rainfall. Okay. So since our chairman already reminded me, so I will go quick. So those are the 3 measurements on the bare side. Okay. Bare side from the crest, middle, and also toe. Okay. You can see the total cumulative over the 4 years. Okay. For the bare side is around, maximum is around 88 millimeter. If divided by 4 average, okay, is only, sorry, for the bare one, actually is 94. Okay, sorry, it should be 94. So divided by 4 is 24. And all those 3 lysimeters, they give you fairly consistent results. Now, how about on the grass side? Okay, these are the grass side measurements, okay, shown in red here, and they are all less than the bare side. This one we also expect. Okay, and the total is 88. Okay. So in other words, okay, and if 88 divided by 4, okay, it's a 22. It's less than the U.S. Environmental Department guideline 30 mm per year. So no matter whether you got grass or not grass, without geomembrane, still meet the 30 mm per year requirement. Now, and with the grass on top, actually reduce percolation by up to 14%, even better. Okay, if you put grass on. Okay, so how about gas? So we install quite a number of gas pressure meter, and again, only at the near the solid waste, we measure a bit of gas pressure. Actually, it's around 0.1 kPa, and this is the Chinese standard 0.75 kPa. So it's far less than the gas pressure, okay, specified by the design guideline, even though without a membrane. All right, so let me go to a conclusion. So in the laboratory, we use recycled concrete, okay. As long as we put in a sufficient contrast in water permeability of this concrete, then recycled concrete can be useful substitute materials for landfill cover. Again, we try the same concept to the field, Over the 4 years, I hope I convince you, okay? And I show you the data. Actually, there's no problem at all, even without using geomembrane. And our rainfall and the rainfall condition in the southern part of China is over 2,000 mm per year. So it's a humid region. Okay. So our free landfill cover system can cover from the dry to the wet weather, no problem. Okay. And grass can help to, based on our own data here, can help another 14% in reduction of water percolation. And 3-layer system can minimize gas emission even during a dry season. Unfortunately, I don't have time to explain more. And if you're interested, there are 2 papers I already mentioned. Actually, by the way, in my extended extract, I provide lots of references if you're interested. Okay. And both laboratory and field data and also theoretical numerical study, again, and I don't have time to go in, can prove our concept. And also very important, especially in congested city, because we use recycled concrete, the friction angle between the materials much higher. So in other words, the landfill slope angle of the landfill can be steeper. So increase the capacity of the landfill. This is also very important. And finally, this are deliverables. Okay, so deliver new vegetated 3-layer, all weathered from wet to dry. Okay, final cover using recycled concrete. By the way, we obtained actually in 2015, we already obtained 2 patents, one from US and one from China. Okay, and the paint one I didn't mention, actually, if you select the plant properly, this all self-regenerated, sustainable, means very low maintenance cost. Okay, and also as I mentioned, because the angle here can be stiffer once you use recycled concrete without membrane. Now remember membrane causes interface problem. Okay, so this one can, if you make it stiffer, that means you can increase the capacity of the landfill. Final words, no membrane is required. Thank you for your attention. And if you're interested in plant-soil interaction, and this is my new book published last year. And thank you for your attention.